Welcome. This is Mrs. Nearing, and in this video, we're going to talk about orbital bonding theory, and we are going to specifically focus on sigma and pi bonding and what that is. So where we are in terms of our AP curriculum, this falls within topic 2.7, where we're looking at the molecular geometry and bond angles and bond energy and bond length and polarity. And it's this last piece here, orbital hybridizations. There's a lot of stuff here in this topic, and we're focusing on this kind of last bit right here. And just going back to the general idea of, valence orbital bonding theory here, is the key idea is that we're thinking of covalent bonds as forming through the sharing of electrons. So that's something we've talked about before. Covalent bonding means we're sharing electrons, and we're imagining this, that the way the sharing happens is when these orbitals in the two atoms overlap. So like this right here shows a bond between hydrogen and chlorine, and we know hydrogen has its only electron is in the 1s orbital. Chlorine has its valence electrons in 3p orbitals. So we can see that when this bond forms between hydrogen and chlorine, we'd have an overlap of the 1s from the hydrogen and one of those 3p orbitals from the chlorine. So that's what we're talking about in terms of like orbital overlap theory. This is what we think is happening. And then right here, in the shared space, this is where they're sharing those electrons. So I drew red dots in here to represent the electrons here. And so that shared pair of electrons, so that shared electron pair is what we think of as a covalent bond. And if they share just one pair of electrons, we think of it as a single bond. We'll see they can also share 2 or 3 pairs of electrons. That would be a double or a triple bond. We'll look at some examples of how that works later. All right, so let's talk about sigma and pi bonding. So it turns out there's kind of 2 ways in which these orbitals can overlap to form bonds. The sigma bond is what we're actually representing right here. In a sigma bond, the orbital overlap occurs what we call on the internuclear axis. That would be this right here. This would be the internuclear axis. It's basically if you drew a line between the 2 nuclei. It's basically we're saying that they're sharing the electrons like right in between these 2 nuclei. So notice how that overlap is happening right here in between these 2 nuclei. And that's what we call a sigma bond. And if you have a single bond, is always going to be a sigma bond. But if you have a double or a triple bond, we know that electrons repel each other. So if we're picturing these, orbitals overlapping, you're probably not going to have like, several orbitals overlapping in the same space, right? That doesn't maybe make a lot of sense because we know electrons are negative, they repel each other. So they probably are not going to want to all occupy the same space here, right? So what ends up happening is when we have like a double or a triple bond, we will have some pi bonding happening. And what happens in a pi bond is 2 p orbitals on nearby atoms, which you can see right here. Here's our 2 p orbitals. They are, and notice how they're oriented perpendicular to that original, that internuclear axis. So, so we have these 2 p orbitals that are perpendicular here, and they're going to overlap in this area, like above or below that first bond. So like if you have a double bond, what's going to happen is here's your nuclei right here. They're going to share some electrons along the internuclear axis. This is what we call our sigma bond. And then if they form a double bond, then what's going to happen is these orbitals up here, they're going to share electrons along this different axis right here. And actually, here's a better picture. I'll just flip over to this one. So you can see the difference here. A sigma bond is they're sharing electrons like in between the 2 nuclei. A sigma bond is happening just kind of like above and below that. So it's like they're still sharing electrons, they're sharing them in a different spot here. So another way to think of sigma bonds, think of it as like a head-to-head overlap. And pi bonds are like a side-to-side overlap. So you've got these. The way we get this shape we're showing up here is it's these 2 p orbitals, which remember look kind of like dumbbells, and they're nearby and they're going to share electrons on those regions. So not along the middle, they're going to share like a kind of the top and the bottom there. And if you're trying to determine what type of bonding is happening, if you have a single bonds are always sigma bonds. So a single bond's always a sigma bond. If it's a double or a triple bond, then like that first bond is a sigma and the rest are pi bonds. So if I was going to go through and highlight, let me highlight these ones. On this one, this is a sigma bond. This right here is a sigma bond, and then this right here is a sigma bond. And then everything, if you have more than one bond, then those additional bonds are going to be pi bonds. So like these ones along here, these are your pi bonds. So like if you have a single bond, it's just one sigma bond. A double is one sigma and one pi. A triple bond is one sigma and two pi bonds. And here's what this kind of looks like in real life. These are some visuals from our textbook, which I think they have really good, I really like their visuals here of this. So notice how if you have like multiple bonds, like in this example, this is formaldehyde, you see how these purple orbitals, that shows the sigma bond right here. So I'll label that. This is the sigma bonding. And we can tell it's a sigma bond because that overlap is happening like between these two nuclei right here, right? And then this right here, the pink area is the pi bond, is that whole pink area. And that's how one pi bond kind of shows up in two locations. So this is just one sigma and one pi bond. That pi bond's like half on the top, half on the bottom. So is the way those orbitals work out. Here's an example of what a triple bond would look like. So in a triple bond, you're going to have these purple ones represent our sigma bonding. And then you see we're going to have some pi bonding happening with these orbitals. And then you would also have some pi bonding happening here with these orbitals. So you might remember from when we learned about orbitals originally in Unit 1, is that the p orbitals, like there's 3 p orbitals, right? And they are along these different axes. So there's one, like unhybridized p orbitals look a little bit like this. I know it's a beautiful picture I drew here, but how we sometimes label them is we label them as one's on the, actually, let's call this the y-axis. So one's on the y-axis, one's on the x-axis, and one's on what we call like the z-axis. So we can think of all these orbitals are kind of perpendicular to each other, and that's why this pi bonding works with these p orbitals, is because they're kind of sticking off at like 90-degree angles from each other. So your initial bond happens along the axis between the two nuclei, and if you have a second bond, it's going to happen at a 90-degree angle up here, and a third bond would happen along this other axis over here. So it's like you have kind of bonding happening along all your axes here, is how this is working with a multiple bond. So you can take some time to look at these visuals to see if you can kind of help make sense of it. Now we're going to do is let's kind of take this idea and go back to orbital hybridization, which we talked about in class and or talked about in another video if you want to go and watch the video on orbital hybridization, and let's see how that fits together with sigma and pi bonding. So remember orbital hybridization, we were talking about the idea that when atoms bond, they actually often will bond using what we call these hybrid orbitals. And the way that you figure out what the orbital hybridization is going to be, your first step is really similar to how you would figure out what the molecular shape would be. And what you want to do is you first want to start out by looking at how many charge clouds are around the central atom. So meaning like in the case of like ammonia, NH3, we would say this has 4 charge clouds around it. So a charge cloud is anywhere where there are electrons. So like in this one, we've got a lone pair over here, so that's 1, and then I've got 2, 3, 4. So it's got electrons on all 4 sides. We'd say this has 4 charge clouds around it, versus a molecule such as this one. This carbon only has electrons on 2 sides. It's got electrons on the left and the right, so it only has 2 charge clouds. And depending on how many charge clouds are around your atom, that's how many orbitals are going to hybridize. So if you have 2 charge clouds, it's going to form sp hybridization. 3 charge clouds is sp2. 4 charge clouds is sp3. So I'm just doing a brief overview of this. I have another video where I go into bond hybridization in more detail, so you can also go back and watch that one. But let's now think about this orbital hybridization and how it fits with sigma pi bonding. So we noticed, like, for example, in the molecule methane, CH4. It's got 4 charge clouds around it. So that means that it's going to hybridize 4 orbitals, and it's going to make these 4 sp3 hybrid orbitals. And there's going to be 1 unpaired electron in each of these orbitals. That's what's going to allow this carbon to make 4 bonds. And if we think about what this would, and notice how all these bonds are single bonds, so that, and we know single bonds are going to be sigma bonds. So we see what's this going to look like in real life is your carbon is going to have these sp3 hybrid orbitals sticking out of it. And then you got your hydrogen atoms over here, and your carbon's going to form 4 sigma bonds with your 4 hydrogen atoms. So this is what that would look like in real life. So we're talking about, well, I guess, you know, in theory, I guess, this is what we're talking about when we talk about orbital overlap theory. We're picturing these hybrid orbitals overlapping with the orbitals from hydrogen. We call these sigma bonds because they happen along the axis between your atoms there. So notice how these are all sigma bonds. Okay, so now let's take a look at this example when you have C2H4. So this carbon only has electrons on 1, 2, 3 sides. So it's got 3 charge clouds. So we're only going to hybridize 3 orbitals here. So we're going to make these 3 sp2 hybrid orbitals. And then we're going to have 1 orbital left over that is unhybridized. Unhybridized. So I have these 4 electrons over here. 3 of them are going to end up in these hybrid orbitals, these sp2 hybrid orbitals. 1 is going to stay up here in this unhybridized p orbital. So let's think about how this fits with sigma and pi bonding. Well, we know that the initial bonds here, let's see if we can label these ones. So these bonds, like these bonds come out of carbon. Carbon has 3 hybrid orbitals. So these ones I just colored in green, these are our sp2 hybrid orbitals. And those hybrid orbitals are involved in the sigma bonding, which you can see over here in this diagram. They're the ones that are in purple in this diagram. So it's got these sp2 hybrid orbitals. And then, oops, I just realized this is actually a different molecule. This is CH2O, but let's just look at this carbon. Okay, so it's got these 3 purple ones. These represent our 3 hybrid orbitals. Those are our sigma bonding. And then we've got this unhybridized one right here. That is your unhybridized p orbital. And notice how it's a double bond. So that's what's going to contribute to our pi bonding right there. So that's the one that's shown in red over here. So each of these carbon atoms has 3 sigma bonds sticking out of it. Those are the purple ones. And then it's going to have 1 pi bond, which is the red one over here. And this is the best visual I could find. So ignore this. This isn't exactly the same as the molecule we're looking at. So ignore this half. Just focus on this half of the molecule so you can see what's happening around the carbons. Okay. Now let's look at another example. What about sp hybridization? So in this example, we got a carbon in the middle. It's only got 2 charge clouds around it. Okay, so 2 charge clouds. So it's going to hybridize 2 orbitals. That's going to be sp hybridization. And then those other 2 electrons are going to stay in these unhybridized orbitals. And we might guess now what's going to happen. So the hybridized orbitals are the ones that tend to be involved in the sigma bonding. And then the unhybridized ones are involved in the pi bonding. So let's see what that looks like here. So we've got, here are our sp hybrid orbitals. So each carbon has 2 sp orbitals, and they're involved in sigma bonding. So notice how each carbon has like 2 sigma bonds sticking out of it. And then it also has these 2 unhybridized p orbitals, and they're going to be involved in pi bonding. So if you're looking over here at what's happening in this model, this bond, and this bond, they are all, the purple ones are your sigma bonds. And then the second and the third bond there, those are pi bonds that are made from those unhybridized p orbitals. So that triple bond in the middle is made from 1 sigma and 2 pi bonds. So sometimes I find it helpful to kind of color code here. And so these visuals are really trying to understand like the theory beyond what's happening here. In terms of like the practicality of what you need to know, often really what you just need to know is this. You need to know a single bond is sigma, a double is 1 sigma and 1 pi, and a triple is 1 sigma and 2 pi bonds. That's like your main takeaway here from this. So, oh, and I should say one more thing. If a resonance structure, if you think back to something else we learned in this unit, is resonance structures. Here's an example of the nitrate ion. There are 3 possible resonance structures. The way that the sigma pi bonding works in a resonance structure is, each nitrogen has 3 sigma bonds sticking out of it, right? So they got 1, 2, 3 sigma bonds, and then there's this extra pi bond that's kind of, a third here, a third here, and a third here. So how we think of that working in terms of this orbital overlap theory is we call this a like delocalized bond. So in a resonance structure, it's kind of like this pi bond is like a third here, a third here, a third here. It's like spread out amongst all 3 of these positions. And that can also kind of give us a sense of why each of these bonds will end up behaving as if they were like 1 1/3 bond, because it's made up of 1 sigma bond and then kind of a third of that extra pi bond that's being spread out here amongst those locations. All right, so I know this is very abstract, but remember this is maybe one of our biggest takeaways is just like what's happening in these different types of bondings. I hope you get a sense of the visualization of what's going on here in terms of these orbital overlap. And you want to know that, let me go back to this visual too, that I think is important, is this one, that this sigma bond is happening between the 2 nuclei, a pi bond is happening like above or below. You only see pi bonding if you have a double or a triple bond. All right, let me know if you have any questions.